Hello everyone. Welcome back to my course Aerospace Engineering, Basics of Aerodynamics. In this video, we will talk about aerodynamics of aircraft fuselage and jet engines. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comments section or reach out to me via the email provided in my profile. Role of the fuselage. The fuselage is the main structural body of the aircraft, housing passengers, cargo, fuel, and systems. Aerodynamically, it contributes significantly to drag and, in some configurations, to lift. Although wings are the primary lifting surfaces, fuselage shape strongly affects overall aerodynamic efficiency. Drag associated with the fuselage. The fuselage experiences skin friction drag due to viscous shear stresses in the boundary layer, pressure drag due to flow separation and wake formation, and interference drag where it intersects with wings and engine nacelles. Aircraft, such as the Boeing 787, use carefully shaped wing body fairings to reduce interference drag. Boundary layer development. As air flows along the fuselage, a boundary layer forms. Near the nose, this boundary layer may be laminar, but it usually transitions to turbulent flow further downstream. Turbulent boundary layers have higher skin friction, but are more resistant to separation. Attempts to maintain laminar flow can be seen in experimental programs such as Airbus's laminar flow demonstrators. However, surface roughness, contamination, and operational disturbances make laminar flow difficult to maintain on production aircraft. Fuselage shape and transonic aerodynamics. At transonic speeds, fuselage shaping becomes critical due to wave drag caused by shock waves. The area rule states that the total cross-sectional area of the aircraft must vary smoothly along its length to minimize drag rise near Mach 1. This principle explains the characteristic Coke bottle shape of aircraft such as the F-16. Lift generated by the fuselage. The fuselage generates lift when the aircraft flies at a positive angle of attack. In fighters like the F-15, fuselage shaping is intentionally used to produce lift and reduce wing loading. In blended wing body designs studied by NASA, the fuselage contributes a major portion of total lift. Supersonic fuselage aerodynamics. In supersonic flight, fuselage aerodynamics are dominated by shock waves and wave drag. Aircraft such as the Concorde and SR-71 use long, slender fuselages with carefully controlled volume distribution to reduce drag and manage sonic boom intensity. Fundamental principle of jet propulsion. A jet engine produces thrust by accelerating air rearward, thereby creating a forward reaction force in accordance with Newton's third law of motion. This thrust results from a change in momentum of the airflow passing through the engine. The engine does not push against the ground or the surrounding air mass. Instead, it continuously changes the velocity and pressure of the air flowing through it. In real engines such as the CFM56 used on the Boeing 737 or the LEAP engine on the Airbus A320neo, thrust is generated primarily by accelerating a very large mass of air through the fan at a relatively small increase in velocity. This design is chosen because accelerating a large mass of air slowly is more energy efficient and quieter. In contrast, military engines such as the Pratt and Whitney F100 used in the F-16 or the F-119 used in the F-22 accelerate a smaller mass of air to much higher velocities, producing higher specific thrust at the cost of fuel efficiency and noise. In all cases, chemical energy stored in fuel is converted into thermal energy during combustion and then into kinetic energy of the exhaust flow. The effectiveness of this energy conversion depends heavily on aerodynamic efficiency at every stage of the engine. Overall flow through a jet engine. Air enters the engine through the inlet, passes through the compressor, where its pressure is increased, flows into the combustion chamber, where fuel is added and burned, expands through the turbine, which extracts power to drive the compressor and fan, and finally exits through the exhaust nozzle, where it is accelerated to produce thrust. In high bypass turbofan engines such as the GE90 on the Boeing 777 or the Trent XWB on the Airbus A350, most of the thrust is produced by the bypass air that flows around the engine core. The core primarily serves as a power generator for the fan. In older turbojet engines, such as those used on early jet aircraft and the Concorde, nearly all thrust came from the high-velocity exhaust jet itself, which resulted in high fuel consumption and noise. Inlet aerodynamics. The inlet is the aerodynamic interface between the free stream airflow and the engine. Its purpose is to capture air and deliver it to the compressor with high total pressure recovery, minimal turbulence, and uniform velocity and flow angle. The compressor is extremely sensitive to inlet conditions, and even small distortions in pressure or velocity can cause instability. In subsonic aircraft, such as commercial airliners, the inlet primarily acts as a diffuser. As air slows down inside the inlet, its static pressure increases. The inlet must accomplish this deceleration smoothly to avoid flow separation. Rounded inlet lips on aircraft like the Airbus A320 are designed to handle crosswinds, rain ingestion, and high angles of attack during takeoff and landing without causing separation. In supersonic aircraft, inlet aerodynamics becomes significantly more complex. Air approaching the engine at supersonic speed must be slowed to subsonic speed before entering the compressor because compressors cannot operate with supersonic inlet flow. This deceleration is achieved using shock waves. Oblique shocks are used first to reduce Mach number with lower pressure losses, followed by a normal shock to bring the flow fully subsonic. A real-world example of advanced inlet aerodynamics is the SR-71 Blackbird. Its variable geometry inlets used precisely controlled shock positioning, and at cruise speeds above Mach 3, the inlet system alone contributed more than half of the aircraft's total thrust by efficiently recovering pressure from the incoming airflow. Compressor aerodynamics. The compressor raises the pressure of incoming air to levels required for efficient combustion. Most modern jet engines use axial compressors, where air flows roughly parallel to the engine axis through multiple stages. Each stage consists of a rotating blade row followed by a stationary blade row. The rotating blades add kinetic energy to the air by increasing its velocity, while the stationary blades convert this velocity increase into a pressure rise. This process is repeated over many stages to achieve high overall pressure ratios. For example, the Rolls-Royce Trent engines used on wide-body aircraft achieve pressure ratios greater than 50:1. Aerodynamically, compressor blades function like airfoils operating in a rotating frame. The angle of attack must be carefully controlled. If the angle becomes too large, flow separates from the blade surface, causing stall. As air moves through successive stages, it becomes denser, requiring smaller blade heights and more precise aerodynamic shaping. In high-pressure compressors, blade tip speeds can approach or exceed the speed of sound. This results in shock waves forming on the blades, increasing losses and reducing efficiency. Designers use advanced three-dimensional blade shapes to manage these effects. Compressor stall and surge. Compressor stall occurs when airflow separates locally from compressor blades, reducing pressure rise and efficiency. Surge is a more severe instability involving large-scale oscillations of flow and pressure, sometimes including complete flow reversal. Surge can cause loud bangs, engine damage, or flameout. Real aircraft have experienced compressor stalls due to inlet distortion, rapid throttle movements, or aggressive maneuvers. Early jet fighters, such as the F-14 Tomcat, suffered from stall issues during high angle of attack flight. Modern aircraft mitigate these risks using variable stator vanes, bleed air systems, and digital engine control systems such as FADEC, which continuously adjusts engine parameters to maintain stability. Combustion aerodynamics. The combustor must sustain stable combustion while allowing continuous airflow. This is aerodynamically challenging because combustion requires low local flow velocities, while the engine requires high mass flow rates. This problem is solved by creating recirculation zones inside the combustor. These zones trap hot gases and act as a continuous ignition source for incoming fuel-air mixtures. Only a portion of the air entering the combustor participates directly in combustion. The remainder is used to cool the combustor walls and dilute the hot gases before they enter the turbine. In engines such as the CFM56 or LEAP, advanced fuel injectors and swirlers are used to ensure uniform mixing and stable flames. Modern combustors are also designed to reduce nitrogen oxide emissions by controlling temperature peaks, as seen in the low emissions combustors used on the Boeing 787. Turbine aerodynamics. The turbine extracts energy from the hot, high-pressure gases leaving the combustor and converts it into mechanical work to drive the compressor and fan. Turbine aerodynamics are similar in principle to compressor aerodynamics, but operate under far more extreme conditions. In engines such as the GE90, turbine inlet temperatures exceed the melting point of the blade material. To survive, turbine blades are cooled internally using air bled from the compressor and coated with thermal barrier materials. This cooling air must be introduced carefully so that it does not significantly disrupt the main aerodynamic flow. Flow through turbine stages involves strong acceleration, large pressure drops, shock waves, and complex secondary flows near blade roots and tips. Even small aerodynamic inefficiencies in the turbine can lead to large fuel penalties, especially for long-range aircraft such as the Airbus A350 or Boeing 777. Exhaust nozzle aerodynamics. The exhaust nozzle converts the remaining thermal and pressure energy of the flow into kinetic energy by accelerating the exhaust gases to high velocity. The resulting momentum change produces thrust. In commercial aircraft, exhaust nozzles are typically fixed geometry and optimized for cruise efficiency. In military aircraft, variable geometry nozzles are used to adapt to different flight conditions. The F-22 Raptor uses thrust vectoring nozzles that not only optimize expansion but also provide control forces for extreme maneuverability. Improper expansion of exhaust flow leads to thrust loss and increased noise. Aircraft such as the Concorde used variable exhaust systems to maintain optimal expansion during supersonic cruise. Engine and fuselage integration. Engine placement strongly influences fuselage aerodynamics. Underwing engines, as seen on the Boeing 737, reduce wing bending loads but introduce interference drag. Rear-mounted engines, such as those on the DC-9 or CRJ series, reduce wing interference but complicate fuselage flow and structural design. Conclusion: jet engine aerodynamics and fuselage aerodynamics together determine how efficiently an aircraft converts fuel into forward motion. Inside the engine, aerodynamics governs compression, combustion, and expansion. Outside the engine, fuselage aerodynamics governs drag, stability, and flow quality. Real aircraft demonstrate that these principles are not abstract concepts, but practical design constraints that shape every aspect of modern aviation. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. What is the primary aerodynamic role of the fuselage in an aircraft? The correct answer is to contribute to drag and, in some cases, lift while housing passengers, cargo, and systems. Question 2. Which statement about jet engine thrust generation is correct? The correct answer is thrust is produced by accelerating air rearward. Question 3. Why are fuselage inlets on supersonic aircraft designed with oblique and normal shocks? The correct answer is to slow the incoming air to subsonic speeds before it reaches the compressor. Question 4. What is the main purpose of creating recirculation zones in a jet engine combustor? The correct answer is to ensure stable combustion. Question 5. How do modern high-bypass turbofan engines, such as the G90 or Trent XWB, generate most of their thrust? The correct answer is by accelerating a small mass of air at extremely high speed. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with aerospace engineering, aerodynamics, and structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with aerospace engineering, avionics, and aerospace systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comments section. I will answer as soon as possible. We can continue to the next lesson and learn about drag reduction techniques. See you in the next video. Bye.